This lesson is for day 8. We're going to be talking about exponential growth and decay in relationship to real-world problems. So we're going to work on all model problems. Our objective for the day is to identify whether or not a word problem represents an exponential growth or a decay, and then we're going to write a function that models that real-world scenario. Then after that, we're going to calculate the output when we're given an input, as well as calculating the input when we're given the output for any particular function. So let's talk about the general form of any exponential function. So we've got two different forms here. Now we've studied this first one, a times b to the x. Now b is your base, and it's the multiplier, right, of a function. Now it looks really similar to this model that we're going to use over here as well. So it's kind of like that idea where we studied in quadratics where we had two different forms. This is the general form for a quadratic, while this form, y minus k equals a times x minus h squared, is vertex form for a quadratic, but both will give you the exact same function. Now, when we deal with model problems, a lot of times we're going to be using this form, a times 1 plus or minus r to the x. So let's talk about what the a value here is and what the r value here is. The a is your initial amount, just like the a value is here. Now this is really like the y-intercept, which is why it's called the initial amount, right? When your function, you're graphing a times b to the x, you're always starting at that a value. This is always 0 comma a, okay? Now over here, same thing, it's still the initial amount, okay? And your r value here is the rate. Your rate, however, should be written as a decimal, though. Okay, now 1 plus or minus r is actually equivalent to b. So you can, I mean, both forms are the exact same thing, but we just break it down as 1 plus or minus r, but it's really equivalent to your multiplier, your base, your b. So the reason why we break this up and put it in as 1 plus or minus r instead of just leaving it as b is because a lot of times in the real world problems that you're given, they'll give you a rate as a percentage. So that's how you can kind of equate that to your base. So you're going to do 1 plus or minus r. Now this exponent here, this variable, is representing in a lot of real world problems the time. So that's why I have this written as the final amount is equal to your initial amount times 1 plus or minus the rate to whatever time period you have. So I don't have a spot to define it, but this is just time. And sometimes you can see instead of x, they'll write, you know, the letter t here for time. Okay, now let's get started on a word problem. So here it says, during normal breathing, about 12% of the air in the lungs is replaced after one breath. Here they tell us that it's an exponential decay function, right? It says, write an exponential decay model for the amount of the original air left in the lungs if the initial amount of air, and I'm going to underline this, in the lungs is 500 milliliters. Okay, so they've given us already two pieces of information. One, we know that there's 12% replacement rate, okay? We also know what the initial amount is. So far, in our exponential decay model, we know that y is equal to a times 1 plus or minus, and in this case, I'm going to do 1 minus r. 1 minus r would mean that I'm taking away that amount, okay? 1 plus or minus r to the time period, which I'm going to call x for right now. So if we're going to just fill in what we've been given, our initial amount is 500. Our rate, which is 12%, I'm going to write that as 0.12. So we want to convert that percentage to a decimal. So my general form for this particular function here, this decay function, would look like this. Y equals your initial amount, 500, multiplied by 1 minus 0.12, raised to the x power. So x and y should be defined as well, so let's do that. Our x value, it's actually equal to, in this case, the number of breaths that are taken, which is kind of like a time, right? That's the independent variable here. And your y output is the amount of air left in your lungs in milliliters. Okay? All right, now the second question here says, how much of the original amount is present after 240 breaths? So what they're telling us now, and this is one of our second objectives here, is to calculate an output when we're given the input. 240 breaths means that x is equal to 240. So I'm going to write out our function here, y equals 500 times 1 minus 0.12 to the 240th power. Now you can simplify this 1 minus 0.12 and stick that in your calculator. So I would recommend doing that, and you're going to get 0.88 raised to the 240th power. So when you put this in your calculator, make sure that you're doing order of operations correctly. So I would make sure that you have this raised to this power here. So here would be the correct way to input this in your calculator, and you can do this all in one line, but 500 multiplied by 0.88 raised to the 240th power. So I have that program where it automatically does that for me, but you can clearly see that you're going to do your exponent first, multiply it by, oops, I did not put in point. Let me go back to that. You don't have to clear that out, you can just hit second insert and then a decimal. You probably already know how to do that, but just in case you didn't. And then I'm going to hit enter here. Now, this is a very teeny tiny small number, okay, really small amount. So what it's saying is that after 240 times that you breathe, there's basically none of the original 500 milliliters of air in your lungs. It's all been replaced by new air. Okay, so this is a teeny tiny amount. That's actually our answer here. So to write that answer, let me show you. It's going to be approximately 2.37 times 10 to the negative 11th power. So very, very small. Okay. I want to show you though how to write this in your calculator the wrong way. A lot of times people put this in incorrectly, and they're not sure why it's coming up wrong in their calculator. So let's say I did 500 and I multiplied 1 minus 0.12. So I put that original value in here. So I did 1 minus 0.12 and raised this to the 240th power. Now, looking at this, even if I give you this problem in your homework or something, your calculator is going to read this, and if you were to read this on your homework, you would read this as 0.12 to the 240th power. It's the whole expression that's supposed to be taken to the 240th power, and your calculator is only going to take 0.12 to the 240th and then multiply 501. So be really careful about how you enter this. This should be in parentheses, okay? If you don't evaluate that and make that 0.88, make sure you put that in parentheses first. So you might get some goofy numbers if you don't. Oh yeah, and another mistake that I see people make is when they type this in, they'll do 500 times 0.88 and then times 240 instead of raising it to the 240th power. So clearly I get a way different number than what I was supposed to get originally. All right, let's continue. Part C says find the amount of breaths needed to reduce the lung's initial volume in half. Okay, so let's think about what this is telling us. They say find the amount of breaths, which means I'm trying to find an x value. That's the unknown. And I want to reduce the lung's initial volume in half. Now, you can go back to the idea that you had 500 milliliters. That was your initial amount. That means that if you want to reduce it to half of that, that would be 250. So really they're asking me, when y is equal to 250, what would be the amount of breaths that it would take for that? So I'm going to set my equation up now as 250 equals 500 times 1 minus 0.12 to the x. Now if you want to isolate x and get x all alone, you would have to divide out this 500 first. So you're really dealing with 1/2 is equal to 1 minus 0.12 to the x power. Now notice that this number here is just half, right? And that's going to be something that you're going to use eventually when we get to something like a half-life problem, okay? Now, to solve this equation, we don't know enough math yet to actually do this algebraically, so you're actually going to need to use your calculator. So let's think about what this is saying here. This is y, which is equal to 1/2, is equal to 1 minus 0.12 to the x. This is what this equation is saying. So I'm going to set up two different equations. One, y is equal to 1/2, and the other, y is equal to 1 minus 0.12 to the x. Okay. In my calculator, I'm going to graph these two functions. So I type in y equals 1/2, which is 0.5, and the other, let me erase this one, is 1 minus 0.12, or you can even just do 0.88, doesn't really matter, to the x power. Okay, and also make sure that you don't write this as times x, make sure it's raised to the x power. Now when I go to graph this, I can't really quite see very much of this in my window here. I can't really see where this is crossing, so I'm going to zoom standard first. You might get a better look at it. Okay, I don't have such a great look at this. So we're looking at y equals 1/2, right? That horizontal line here is going to be the intersection of this exponential decay model and that graph here. So let's try to zoom in where we can see where that's occurring at. So I'm going to go to my window, and instead of going all the way up to 10 on my y max, I'm only going to go up to 3. Okay. Also for my x min and x max, I am going to shrink it a little bit so that I'm only focusing on where it is going to cross. So I'm going to go to 0, and let's keep it at 10. The reason why I'm putting the minimum at 0 is because you can't have a negative number of breaths. So that's why we're dealing in the real world. I don't really need to see that being a negative value. Same thing with my y min. Okay, so let's go to graph this. And now I get a much better look at this particular function. Okay, now I want to find the intersection here, so I'm going to calculate second trace here and go down to intersection. Hit enter, 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 and I end up with 5.422, comma 0.5. So this point, okay, the intersection. Let's make sure we write down what we did. We hit second calc intersect, and we get the point 5.4 ... there's more to that, comma 1/2. So this means that that's approximately 5.4 breaths for that initial amount of air to reduce to exactly half of its volume. Okay, question 2 is a financial question, which we'll see a lot in pre-calc, but also in the real world. So this is probably one of the more applicable real world situations that we are going to study, just because it relates so much to like what you do when you invest money in bank accounts, in your home, in mortgage payments, all sorts of stuff. So anyhow, here we go. It says you deposit $500 in an account that pays 8% annual interest compounded yearly. What will the account balance be after 6 years, and when will you have $1,200? So this is clearly going to be an exponential growth, because you're hoping that when you deposit money in an interest-bearing account that you're going to gain money from it. So this is a guaranteed 8% annual interest that you're going to get after a year. When it says compounded yearly, that means that after a year, they'll give you 8% back of what was in the original account. So we know that this is going to be a growth, because they're going to add money to your account. So we have, we first should define our variables. X is going to be the number of years in the account, so the amount of time that you have it, placed into the account, while y is going to equal your account balance. Okay, and this function, since it's a growth, should be my initial amount, $500, multiplied by 1 plus our rate. Now for 8%, make sure you're moving that decimal 2 spots. I often see students just write an 8 in there, or write it as 0.8. Make sure you're moving that decimal spot 2 to the left to get 0.08. Okay, and then we'll raise that to the x power. So this is the general form for this model, and we want to answer the first question that says, what's the account balance after 6 years? So this is x is equal to 6. Now we have y equals 500 times 1.08 raised to the 6th power. This is something that you can easily type right into your calculator, so I'm going to show you what I ended up with. Now, if you answer $793.44, that's typically what we would answer, because we would ask you to round up typically, right? But this is a bank. Now, if you think about what a bank is going to do, if they constantly rounded up the value of interest that they're giving away to people, they'd lose a lot of money. So they actually keep track of all of these decimals, and they don't give you that next penny until you really earn it. So in this case, the account balance that you would see is $793.43. So you actually don't want to round up when you're dealing with interest questions, especially as it pertains to a bank or a loan. Okay, so you get an answer of $793.43. So the moral here is don't round up. Okay. The next question says, when will you have $1,200? So in this case, this is y is equal to $1,200. Find what x is equal to. So really, if I wanted to plug this in, I'd have $1,200 is equal to 500 times 1.08 to the x power. Now before, what I did was to isolate that x value, I divided the 500 first, so I ended up with 1200 over 500, and the problem before it ended up being right, y equals 1/2. Instead of doing that though, I'm just going to go ahead right away and plug in these two lines, because technically I know that y is equal to 500 times 1.0 to the x, right? This is my original function, and this is now the y value that's a line. So I have a growth. This is my growth function, and this is just a horizontal line. I want to know where those values will cross. I want to know the intersection, because that will tell me the exact x value, okay? So in my calculator, I typed those values in so that I could do this real quickly with you. But remember, our window was needing to be adjusted here. When you go to your window, you do want to keep your x min and your y min at 0, because it's still dealing in the real world, so you don't really care about anything before that. Your x max, since we're only going for about 6 years, don't make this an entirely huge number. A lot of you guys want to make this huge just because your y output is big here. Let's say, I don't know, if we're not really sure, let's put 30 years in there, because that's not too crazy of a number, but it's still large enough to try to see if that intersection occurs after 6 years, okay? And it does make sense that it would occur after 6 years, because after 6 years you only have 793, and we need to get to 1200, okay? So for my y max, I'm only putting 1500 in here because I need to get to a y of 1200. So this should be a pretty decent window for myself. So let's take a look. We should see that curve. Oh, and there it is. So I do have a pretty large x value. This is all the way up to x is 30 over here, right? That's the right-hand side of this screen. Now, you could have put in a lot lesser amount, but maybe that intersection would have occurred after 30. So, you know, it's kind of hit or miss. You just keep trying. But let's hit second calc, intersect. First curve, second curve, guess, just hit enter, enter, enter. And we get 11.375, comma 1200. So to interpret what that point means, we get the coordinate. And again, I want to write second calc, intersect. Make sure you're always telling me what exactly you put in your calculator in order to do that. You get the coordinate 11.38, comma 1200. Now that coordinate is saying that you get $1,200 after 11.38 years. Okay, so this is approximately 11 years and 4.5 months. Now to find what that 4.5 months, all you need to really do is, this means years, right? This is the decimal place. You can multiply 0.38 times 12 months to figure out the number of months, and then you'll end up with that value, 4.5 months, okay? So after 11 years and 4.5 months, you finally have $1,200 in your account. All right, let's work on the back page here. I'm going to do just a couple things with you guys and let you guys practice some of this so that you can practice just inputting things in your calculator, okay? All right, in 1985, there were 285 cell phone subscribers in this town. The number of subscribers increased by 75% per year after 1985. How many cell phone subscribers were in Centerville in 1994? Okay, so our initial amount of cell phone subscribers was 285 in the year 1985, okay? So if we're going to define our variables, I want to let x equal the number of years after 1985, because that's when this whole idea is starting, okay, about cell phone subscribers. So we're looking at the specific time after 1985, and then y is going to equal the number of people or cell phone users. So number of cell phone, I guess subscribers is the word that they're using. So this is going to be a growth because it's telling us that it's increasing by this amount, 75%. So our general function is going to be y equals 285, because this is our initial amount of cell phone subscribers, multiplied by 1 plus our rate here. It's going to be addition because it's a growth. And we're going to change that decimal, or that percentage into a decimal by moving it to 0.75. And then we're going to raise that to the x power. Now, this question specifically asks how many cell phone subscribers were in Centerville in 1994. So this is saying if X is equal to a certain amount. What's the Y output, right? Because we're looking for the Y. How many cell phone subscribers would mean you're looking for the Y. So this must be an X value. Now, to figure out what X is equal to, make sure that you're taking 1994 and subtracting 1985, and you're going to get 9 years. So you have to input 9 instead of 1994. So that's a common mistake. People will plug in that, and then it's not 1994 years, okay? It's only 9 years. So you can go ahead and plug that in and solve for that and check with the key, and make sure you're always using units also, okay? In number 4, it says during each round of this tennis tournament, half of the players are eliminated, and then how many players remain after 5 rounds. So here you have to really understand the context of this. If half of your players are eliminated, that means it's a decay, okay? And your rate there is basically 50%, right? If half are eliminated, your rate is 50%, so you're going to have to move that decimal twice to get 0.5. So go ahead and try that one. And then number 5 is really similar to that first question that we worked on. Try to make sure that when you get to part B here, that you get the correct number of months also. Okay, I want to see you making sure that you can do what we did up here when we found that was 4.5 months. You have to take that decimal and multiply by 12 months in order to find the number of months there. Okay, now, just to recap, you're writing an exponential growth or decay. In a model problem, we're using this particular idea, that function here. And it's really straightforward, whether it's a growth or a decay, usually based off of the context of the problem. You're going to be asked to find an input when you're given an output. So that was more like actually part C. And you're going to be asked to find an output when you're given the input. So like if they give you the X, find the Y. If they give you the Y, find the X. Now this is definitely the harder skill. Finding the X value here is harder because you have to go back to your calculator and do this whole idea of finding the intersection. All right? But that's the end of the lesson. Make sure you do practice these problems here. Don't just copy them from the key because you're not going to get anything out of it. So do practice that and make sure that you're ready for tomorrow to work on some additional problems. All right, nice job. See you tomorrow.